8 years since we have initiated this journey into dental FEM analysis. So without wasting the time, I would like to initiate the workshop. So this is the agenda of the day. So we'll be in introduction to the panel, then we will be giving the excellence award to our prominent faculties, and then we will be just kicking off a live workshop on dental FEM, and then we'll have a Q&A session. So this is the schedule of the day. So we'll go accordingly. So just that for the opening or ceremony, I would like to invite our director, Nasha Gupta. She has got enormous experience into analysis field. So over to you, ma'am. Just if you can switch on your video and just cherish us on the start of this journey.
Thank you, Atul. Thanks a lot. Hope you are able to hear me and see me as well, right?
Yes, yes. Good.
Okay. Good morning, all. It's a delighted moment for all of us, and especially for us as we are hosting our 10th workshop, and we are really happy to see you all.
Can
we see you all? Can we see you all if we can just, on our videos? So it will be really nice to see each and everyone on the screen, and kindly mute yourself if somebody is doing the other task as well at the same time. Good morning, all. I would like to welcome all of you, and especially I'll be extend my warm welcome to our chief guest, Shri Govind Sharma ji. He is and we are honored to have you here. So can we hear you, Govind sir? Are you there?
Yes, I am there.
We would like to welcome you, sir.
Okay.
Good morning.
Thank you.
And we are delighted to have you over here.
Okay.
We are also privileged to welcome our chief guest, and along with that, the distinguished guest speaker and the subject matter expert into the dental sciences, who has made a significant contribution in their respective fields. I would like to welcome Dr. Namita Kalra. Good morning, ma'am. Dr. Chandrika Sorti, Dr. Prashant Karni, Dr. Rita
Satish
Jain,
is giving me homework which needs to be done urgently.
Dr. Siddharth S.P. Behera, and Dr. Kumar Amit. We welcome you all, sir. And today agenda for the workshop is just to know more insightful of the dental FEM analysis, where we are trying to capture all three branches. The one will be prosto, the other will be ortho, and the third will be pedo. So here we would like to cater all these three branches, where we will be talking about the milk tooth and its analysis. We will be talking about the aligners and how it is important and how significantly it has done the contribution in the dental analysis. Apart from this, we would be catering the dental implant as well. And we are looking forward for the fruitful session today. I would request you, while the session will be going on, and if in case any of the query will raise or any of the question will be from your side, kindly just write it in the chat box. So at the last of the session, we can cater each of them one by one. Thank you all. Thanks a lot. Over to you, Govind sir.
Okay. Good morning, everyone. It's a pleasure to be here at this workshop focusing on finite element analysis in dental implantology. It's fascinating to trace the evolution of dental implants from early attempts using materials like shells and bamboos to the highly predictable treatment we have today. Ancient civilizations explored various materials, including human and animal teeth, ivory, and precious metals. The pivotal moment arrived in the 1960 with the Brenmark's groundbreaking discovery of osseointegration, which truly transformed the field. Now, titanium implants and sophisticated CAD/CAM restorations are standard practices. Looking ahead, the application of finite element analysis in dental implantology holds great promise for enhancing implant design and placement. By predicting stress distribution within dental implant and the surrounding bone through computer modeling, FEA is set to become even more integral to clinical practice. This will be facilitated by progress. This will be facilitated by progress in software, hardware, and the integration of artificial intelligence. Ultimately, these advancements will position FEA as an essential tool for dental implant practitioners, empowering them to make more informed decisions and achieve improved clinical outcomes for their patients. I trust that this summer dental workshop will provide a valuable and unique platform for dental scholars to learn from leading experts and collaborate on the future direction of FEA in dental implantology. I am confident that this workshop will be enriching learning experiences for all participants. Thank you, and I look forward to embarking
I'm
on
not,
this
I've got
exciting
work.
journey
You
of
call Rishabh and
discovery.
I'm out in duty
Thank
room.
you.
They're sitting in there simply.
Okay, thank you. Thanks a lot, sir. Thanks for your kind words and your detailed insight in depth, uh, you know, knowledge into every field, I would say so far. So thanks a lot, sir. And we'll move ahead from here. So, I'll So let me just introduce ourselves. Like we AnaMac Design, we are not only into dental analysis. We are into various domains. So we do seismic analysis, we do structural analysis, we do the analysis for communication tower. Recently, we just like to highlight that we are doing the analysis for Vande Bharat as well. So their entire structural analysis and their crash analysis, everything we are doing into that domain as well. Moving ahead, these are the some of the premium clients of, through which we have worked. On left hand side, these are the industrial client. On the right hand side, there are various universities and colleges whom we have helped for doing their dental FEM analysis, and we have got the so many colleges registered for the workshop and for the dental analysis study with us. So if I move on to the next slide, these are the few colleges where we have signed the MOU, and we provide some funding. We have a funding association with these colleges like SGT Gurgaon, KLE VK Institute of Dental Sciences, Navodaya Dental College, Adi Parashakti, Karpaga Dental Sciences. And recently, we have signed just, MOU with SB Patil Institute of Dental Science as well. And we have the prominent faculty, Siddharth sir, as well today to cherish us on the dental analysis today. So, moving on to the Excellence Award. So we have the prominent faculties who have done the extensive work toward the in the field of dental analysis, and they have extensive experience. So it's our privilege, and we are really obliged to honor these faculties. So there's some of the faculties who are agree to have their presence today is Namita ma'am. Namita Kalra is having an extensive experience, so we would like to, present the Excellence Award to her. Coming to next, we have Chandrika Sarvokatti ma'am from Navodaya Dental College. We would like to, mm, uh, um, and the next is Rita Jain ma'am. He is having an extensive experience into dental analysis from Firozpur Genesis Dental College. Next, we move on to Prashant sir. Prashant sir is having an extensive experience, and he is part of our one of the colleges where we have MOU with us, from the CARES, KLE Dental Sciences. And we have Dr. Kumar Amit, who has been doing the complex study for into the dental analysis field. He is from Shri Banke Bihari Dental College. And we have this Siddharth sir as well with us today. So where we have signed the latest MOU with the SP Patil Dental College. Now, I would like our prominent faculties just to cherish with their, a few words. So I would like to request Namita ma'am, if she can, just unmute and just switch on her video and just provide her insight towards the dental industry about her experience so far. She's having extensive, vast experience into dental field. Yeah, Namita ma'am, I would like to hand over to you now for your kind words. Namita ma'am, you have to unmute yourself.
मैडम ने लेफ्ट कर दिया
Yes.
is
Yes, it is now audible.
Mr. Govind Sharma. He's very knowledgeable, and Dr. Abhilasha Gupta is so dynamic. I'm very happy to say that I am grateful for being here with all of you. And finite element analysis is, of course, a very upcoming and significant research field, a tool, and it's helping us with all biomedical analysis, biological research, and it is the ultimate method in modeling complex structures and analyzing their mechanical properties. The role in implants is to study the stress patterns in various implants, to study the biomedical properties of implants, and also for predicting the success of the clinical conditions. To study the stress patterns in various implants makes it easier to predict, to promise a patient what he should get after spending so much time and money with the dentist. And the one can understand the simulated traumatic loads. Of course, it is all in vitro, but it helps us to understand a lot about what goes on. I hope you can hear me. Role of FEM. It is gone. It is lost. Yeah. Should I do it again?
Ma'am, can you speak now?
Yeah. I'm going back. I'm going back and getting into the meeting again.
Yeah, sure. You are audible. You are audible. Your video is fine.
If I'm audible, then I can just continue.
Yes, please.
Role of FDA, role of finite element analysis is mainly in maxillary obturators, apart from implants, post and core restorations, periodontal ligaments, and in trauma patients, especially in the maxillofacial trauma. FEA software is a type of computer program used to stimulate and analyze the behavior of physical objects or systems under various conditions, such as stress vibrations, heat transfers, and fluid flows. These are the functional parts of oral physiology which we cannot restore without the help of FEA. It breaks down complex systems into smaller, simpler elements, us to accurately predict how they will react to whatever process we role in trauma, childhood dental trauma, and also in syndromes where there are multiple teeth missings, like cleidocranial dysostosis, where you might need an implant, and other patients where there is a loss of hair and loss of teeth. And there are many syndromes, and these children helped But the FEA or FEM has to be brought down to their level of acceptance and to the level of availability. I'm sure with the passage of time, more and more patients will benefit and more functional dentistry will be practicing at the moment. That's all I have to say. Thank you very much. Thank you to the admin. Thank you, Dr. Gupta. And thank you, Dr. Sharma. That's all. Thank you.
Thank you, ma'am. Thanks a lot for your kind words.
Thanks a lot, ma'am. Thanks for your precious time and your extensive knowledge have cherished the scholars and the upcoming researcher. Thanks a lot, ma'am, for your time. Let us move ahead with our the second prominent faculty, Dr. Rita Jan, ma'am. Rita Jan, ma'am, can you please unmute yourself and please just cherish the audience with your kind words and with your extensive knowledge into this field.
Okay, thank you. It's a very good morning to one and all present here. First of all, I would like to thank Abhilasha ma'am and Mr. Atulji for giving me this opportunity and share my views. As we stand at the intersection of the engineering and dentistry, so finite element method has emerged as one of our most powerful tool for understanding and predicting dental biomechanics. So FEM in dentistry typically covers how this engineering simulation technique is applied to analyze stresses and deformations in dental structures and materials. So there are six basic different steps in FEM. First is modeling geometry, second is meshing, third is material properties assignment, and fourth is boundary conditions and solving using FEM software, and last is post processing, analyzing results and stress, strain, and deformation. So there are many applications in dentistry: implant design and placement, crown and bridge, load analysis, orthodontic tooth movement, TMJ, stress analysis, bone remodeling, prediction, endodontic post and core design. So there are many advantages of FEM in dental research. So accurate prediction of biomechanical behavior, virtual testing of treatment plans, and reduces the need for clinical trials or animal models. Basically, we don't need here animal models. So we can do the study on the CAD model, 3D models. But certain limitations of the FEM study also, it requires accurate geometry and material data. Results depend on mesh quality and boundary condition, and it is computationally intensive. There are many software used in this technique: ANSYS software, Abacus, COMSOL, Multiphysics, and SolidWorks simulation. So looking ahead, we are integrating FEM with artificial intelligence and machine learning to create predictive models that can instantly analyze patient-specific anatomy for CBCT scans. So the convergence with digital workflows from intraoral scanning to CAD/CAM manufacturing means FEM will soon be seamlessly integrated into our daily practical routines. So FEM represents more than just sophisticated analysis. It embodies our commitment to precision medicine in dentistry. So thank you very much. So,
Thanks a lot, ma'am. Thanks for your time and cherishing the audience with your extensive knowledge into dental FEM analysis. Now moving on to our next prestigious faculty, Dr. Prashant sir. Dr. Prashant, I hope that you are there. You have been with us for so long, so I would just request you to unmute yourself and just you know.
Yeah, sure. Just give me a second.
Yeah, sure, sir.
Am I audible?
Yes, it is audible.
Yeah. Good morning. It gives me an immense pleasure to be a part of this dental analysis summer 2025. And I'm grateful to Dr. Abhilasha Madam and Mitul sir. And today we delve with fascinating cutting edge technologies, which are from the dentistry as well as it is from the engineering. So since I have been trained in the 3D experience, the Dassault company, so that has been from the German, and I was lucky enough to be in the part of that. Almost we have trained for 7 days, and we have done the FEE and FEM both, and it's mind-boggling because engineering things and technology, which has been given us so much of opportunity to build and to do a patient care in a very different manner. So the dentistry is always evolving the newer technology, newer materials. Yes, definitely the FEM and FEA analysis, definitely in the terms of as I'm a prosthodontist, I'm looking for the fixed partial dentures, removable partial dentures, and implant dentistry per se. And this can be included in the maxillofacial as well as TMJ. So the AnaMac, which have been already consistent with we have the MO with the AnaMac, and they are doing really great job, and they are insisting for research work as well as we have been doing some of the research activities along with the AnaMac. So I'll be grateful to you, and as my senior colleagues have already expressed their views on the FEA and FEM. So I don't want to again say the same thing. So in the future slides, the Abhilasha madam will be taking over it. And thank you so much. And please take this workshop as an research innovative methods where we can really do wonders when we do such kind of studies and more innovations along with this technology. Definitely wish you all the best, all the students. And thank you all, ma'am. Thank you, sir.
Thanks a lot.
Thank you, sir.
Thanks a lot
Thanks, sir.
for your time and just cherishing our audience with your extensive knowledge into this study. And we are really thankful to you and your entire department who are working with us on the innovative studies we are doing into dental FE. Now, moving on, I would like to invite Dr. Amit sir. Amit sir, I know that you are facing some problem in the video, but I hope that your audio will work for us today. So just please handing over to you. Hi sir, are you able to unmute yourself? Amit sir, are you there? We are not able to hear you.
Might be he is facing some difficulty in the network, so we can move on to the next. And as and when sir will be back, he will be addressing to us.
Okay, sure, ma'am. So moving on to other prestigious faculty, Amit sir, just let me know if we are able to hear you. So we will definitely like to hear your kind words on the dental FEM as well. Moving on to Dr. Siddharth sir. Siddharth sir, thanks for joining today and cherishing us. So I would just request you to please unmute your mic and video and just uh, provide your more insight towards the dental FEM.
Sir, am I audible?
Yes, yes, absolutely fine.
Yeah. Everyone, I just don't want to repeat what the other peers have spoken about, but I just want to stress on what is the need of FEA right now in implantologists. We are evolving on the prosthetic part more rather than on the designs of implants. So rather than going with complex in vitro studies and in vivo studies, FEA is giving us an opportunity to cut short those things and evaluate the stress patterns on the mechanical components of the parts of the implants. So that way it will be more helpful for a prosthodontist or any general dentist to understand what kind of prosthetic design we want to give. That is what we are looking into, because FE is basically looking into the isotropic properties of any material, but it's the time now to look more into the anisotropic properties of the material. So I guess that's the future trend in implantology. So we need to explore into it, and FE is the right tool right now with evolving digital dentistry. So if we can club both together, then it is definitely going to be fruitful for everyone. Sir, you can go ahead with any other peers who was to throw some light on FE. Thank you.
Sir, I would like to just add few
Ma'am, we are not able to.
lines on you, your thoughts. First of all, thank you very much.
Hello.
Hello, sir. Thanks a lot. I have requested Dr. Amit sir to switch to other device. I hope that we are able to hear Amit sir. Amit sir, are you there? Hello. I think we are not that much lucky to hear him. I was just talking to him that if he can join with some other device. Anyway, like moving on to the next is the one of the prominent faculty, Dr. Chandrika ma'am. So Chandrika ma'am, can you please unmute yourself, and we are having your slides to take over. Just let us know when we would like to move with your slides. So
yeah, you
just
can.
open it.
Thank you very much. Yeah,
Yeah.
you can start with the.
Yeah. Okay.
Yeah. Yeah. At the outset, I would like to thank AnaMac Designs for giving me an opportunity. Yeah, let's understand FEM, orthodontics. Orthodontics is a branch of dentistry where we deal with correction of malpositioned teeth and jaw. Because aesthetics is of great concern in nowadays, so we have to treat patients orthodontically to create beautiful smiles and increase the confidence of an individual. We have various appliances to treat the malocclusion. Fixed orthodontic appliances, as we all are very much aware, whether it is in the labial or lingual. But nowadays, clear aligners has taken over most of the orthodontic appliances. So we need to understand very well how the appliances work. Can I go to the next slide?
Yeah, sure.
Yeah. So orthodontics is a branch where we do not prescribe medicines. Force is only medicine here, which is applied onto the tooth surface to bring about various kinds of tooth movement with various different kinds of appliances. So force has biological effect on the periodontal ligament and alveolar bone, thus bringing about tooth movements with selective osteoblastic activity and osteoclastic activity, wherein we have remodeling changes in the alveolar bone. Along with this, we also biomechanical changes where stress-strain relationship is very important, and that is very well understood because of the engineering tool, that is FEM, what has been introduced, and AnaMac Designs will definitely help us in all such kinds of research activity which is to be carried out. Next slide, please.
No.
So orthodontics is a very fascinating and challenging field, of course, but wherein we don't understand biomechanical effects of any force which is applied. So we require rational thinking. For that, we need to have various research activities which are carried out to understand how actually the force works.
Then
And
you'll get
what
in one page only.
so analytical method is systematic review, experimental method where we need various number of patients. Numerical method, that is finite element analysis, gives us what biomechanical changes or effect
In one page,
happens in jaw and teeth when
absolutely.
any force is applied onto tooth surface. So finite element analysis, next please. Next slide, please. So it is a powerful tool for us as orthodontists, which was first introduced by Farha in 1973, and it is being continued. It is computer-based numerical method wherein mathematical representation of actual problem which is faced in the oral cavity is seen. It helps predicting how a structure or a tooth behaves when force, load, or stress is applied onto it. and what is the kind of deformation of that structure which takes place because of the load which is applied. This simulation of the oral cavity in the digital way. Okay, basically, it is finite element is discretization or breaking down of your structures into smaller, simpler elements, which are known as finite elements, which are connected through nodes. Here we can see the finite element model, which is nodes which are elements connected through nodes, wherein we can see the structure, how it actually behaves when force is applied. The blue is minimum force, and the red is where the maximum stress is seen on the structure.
Right.
Next
So what
slide.
I'm showing you, right?
Next slide, please. Next slide. So here, when we come to the material property assignment, once the elements are broken down and nodes are there to connect, each element or each structure is assigned with the material property depending upon Young's modulus and Poisson's ratio, whether it is tooth, periodontal ligament, bone. All this is done by finite element software. Yeah, please, next slide, please. So how does the workflow of orthodontic FE model takes place? First is we need to acquire patient-specific information, which is through CBCT, DICOM images, intraoral scanners. Here we can take only one patient for CBCT, which will be helpful for various different designs which we create through FEM model. Then we will have to virtually create all structures. They are created virtually with high accuracy. But whatever kind of appliances, here it is shown as clear aligners or any different aligners, we have to assign the loading condition. Then this will help in simulating an orthodontic tooth movement. So we generate 3D virtual model. AnaMac designs will help us bringing about all these to carry out various research activity, and it is quite helpful for all students and faculties who are utilizing this, and it will be of great help. The last and the final thing what is done is post-processing, which is interpretation of results. Next slide, please. This is a very important part where we have to interpret the results by measuring total deformation of the structure, which has happened due to the load applied, and also the overall stress, which is von Mises stress in megapascals. Total deformation is the displacement or change in shape of the structure under the applied load, which is very important to understand what happens to the area under stress when we are applying through any of the appliances. Overall stress is the combined effect of all the stresses, and this will determine whether the material or the structure will permanently deform under the given load, which is depicted by red color, and that is supposed to be not conducive to the oral cavity. Thus, FEM will help us in analyzing stress-strain relationship of an orthodontic appliance, any kind of appliance for that matter, without the need of any patient, wherein we will apply the force directly on the patient. This is totally on a virtual model. It can definitely be implemented in many of the patients, various different designs. Next slide, please. So advantages of FEA is more comprehensive it involves many things and it gives us results, improved design, increased productivity and revenue. It is non-invasive and we need not use any patient. Results can be easily interpreted once it is done by our software engineers. It minimizes the requirement for laboratory testing, animal study, case studies, and less time consuming, which is otherwise a long way to go when we apply any force and the results. So no extensive instrumentation is required. Some shortcomings are supposed to be taken care, like when material properties are assigned or loading conditions are applied, we have to be very accurate, otherwise inaccuracies may occur, and computational errors as it is in any computer related things, and it also depends on software and the personal working, but AnaMac designs will definitely help us in doing that to the best. Next slide, please. So to conclude, I would like to say finite element presently is a critical research activity in dentistry, particularly in orthodontics, implantology, and restorative dentistry, allowing us to analyze the stress distribution, how it actually occurs, predict biomechanical behavior, simulate clinical situations without the patient, thus helping us with different designs for the treatment and various other treatment planning. Next slide, please.
Okay, ma'am.
I would like to thank the admin, Mr. Govind sir, madam, for giving me an opportunity, and I hope it was informative. And for the student community especially, because they will be the ones who will be continuing with the research activity, and it is really helpful as for us faculties are also concerned. Thank you.
Sure, ma'am.
Thank you, ma'am.
Thanks a lot, ma'am, for your precious time and enriching us with your extensive knowledge into the dental FEM analysis. I think we have Dr. Kumar Amit sir again with us. Amit sir, are you there? Hello. Yeah, Amit sir, just unmute yourself, please. Amit sir, you are still on mute. It's showing mute, sir. It's still showing mute. So if you can unmute yourself. No, we are not able to hear you. Sir, it is still mute. Let me do one thing. Let me dial you and let's see if we can able to. Hello, sir.
Yeah, hello.
Are you able to hear me now?
I'm trying to.
Yeah, hi. We are having Amit sir with us. So Amit sir, yes, we would like to listen you as well on this forum. Thanks a lot for your time. Yes, over to you, sir.
Am I audible now?
Yes, yes, yes.
And am I visible now?
We see the visibility is still not there, sir, but you can.
Okay, fine. Okay. Let me not waste your time anymore. Thank you, admin, and thank you, Abhilasha ma'am and team AnaMac for your invite. And I'm pleased to get this opportunity to share my views about FEM in this workshop. I know that the faculty and the team conducting this workshop are much more experienced, and they are the apt people to talk about the topic, its intricacies and technicalities. But as an orthodontist, I would like to say that when I started off my career post PG even, until recent years, I had very limited knowledge about FEM. And I considered it as a computer-generated model to study stresses in teeth and surrounding structures. And I felt happy about the fact that the lab does majority of the work for us, thereby reducing my time and effort. But as I got into the details of FEM for some of my research projects, I developed more interest into the subject matter. As an orthodontist, we all know that we move teeth to correct malocclusion, and orthodontists have been doing this for the past more than 100 years. But the biggest irony is that we are still trying to figure out the underlying reason and the exact mechanics behind tooth movement while using different appliances. Also, throughout the years, different orthodontic appliances which have been developed have been first tried on patients to understand their biomechanical efficiency. But this should have been done the other way around, which means appliances should have been designed with known biomechanical properties and efficiency, and then they should be used in patients. So in this regard, FEM can prove to be a very important tool. It's an important mathematical tool, or we can say an engineering tool, which can help us in this regard. Orthodontic tooth movement is a radial phenomenon which has a complex geometry. We are aware that when we apply forces in the range of 20 to 150 grams over a prolonged period, orthodontic tooth movement takes place. And when higher forces of more than 300 grams are applied, orthopedic changes take place. Still, we come across problems like root resorption, lesions, penetrations, etc. It is because of the fact that the tooth, the PDL, and the periodontium has complex geometry, and the forces which we apply might not be transmitting the way we desire because of the complex geometry of these structures. So, FEM plays an important role in this regard. It helps predict and visualize the stress distribution and the formation of tissues during tooth movement. In orthodontics, I feel there is much more application of FEM, like for simulating tooth movement, for analyzing stress distribution, even to predict bone remodeling, to evaluate different treatment modalities, and to understand the biomechanics of tooth movement. For the development of new devices, FEM can prove very vital. Nowadays, aligners are becoming quite popular, but their use in complex cases is little limited. Aligners adapted on tooth, means along with their tooth and attachments, they make a even more complex geometry, which has to be understood to understand the biomechanics of aligner treatment. So much more FEM studies in this regard has to be carried forward. And one biggest limitation of FEM is its integration with AI. So I hope once AI is integrated with FEM, that can definitely improve the predictability and accuracy of aligners. With this, I conclude my talk. Thank you once again, the organizers, for this opportunity to share my views on this platform.
Thanks a lot, sir. Thanks for your views towards and bringing the aspects of AI as well into it. And we definitely, as we move ahead, definitely will take care and with the visibility of you people are having into a having a thought bringing to AI into it definitely will help the future fraternity and all the users of dental FEM analysis. Now, without wasting time, I would like to start. I would like to ask Rahul, sir, who is the one of the experienced FIA engineer into dental FEM analysis, to take over to the journey with the live workshop. While explaining in the software how the analysis used to take care with different models into the ortho and prostho streams. Rahul, sir, are you there?
Yes, sir. Hi, Atul, sir. Can you hear me?
Yes, I can hear you very well. So let me just make you the host for the the remaining journey of this. So just give me a second. Let me see where exactly Rahul sir is, Doctor. I am not able to view you in the list. EQ. Can you just chat in chat box? You are there, right?
Yeah.
So just okay. I'm able to find you. So I'm just making you the host now. So what do you just share
Thank you,
your
Atul, sir.
screen from the slide of the dental FEM analysis. Now, thanks a lot for joining into this journey. Now over to you, Rahul.
Thank you, sir. I'm sharing my screen.
Yeah, sure.
Yep. Can you see my screen?
Yeah. So can you put into the slide mode?
Yes.
Yeah.
Well.
Yes.
One second.
Yeah, now it is fine.
Well, yeah. So, good afternoon, everyone. So I'm excited.
Perspective on the timing of the treatment, alternate treatment. मतलब उनको किस एज में मतलब क्या नॉलेज है मतलब हम थर्ड ईयर फाइनल ईयर फिर हमें इंटर्न्स को या
I request
एवरी डेंटिस्ट जो है उनको जाके
people to mute themselves so that we can have a
हाँ पहले तो ये सेलेक्ट हो जाए.
Rahul, you need to mute her, Dr. Sunanda. Dr.
Sorry.
Sunanda. No issue, ma'am, please.
All right. Good afternoon, everyone. So I'm excited to be here with dental professionals to share something that connects engineering with your world of dentistry, that is finite element analysis or FEA. You can see here CAE, FEA, FEM, FE simulation, virtual simulation. So the same field has been addressed with different names. So you might come across all these names, but they address to one single subject that is we can call with any name. So yeah. So now I know that you might be thinking like FEA. That sounds like something for aerospace engineers or car designers, and you're right. It is used in those fields. But what's fascinating is how FEA is also quietly transforming modern dentistry. So few scholars has already touched upon the topic. So, but as a mechanical engineer and a dentistry enthusiast, I would like to share a few interesting facts and insights from my perspective. So, whether it's analyzing the stress on a dental implant, improving the durability of braces, or designing crowns that last longer and fit better. So FEA helps us simulate how the real world forces affect the dental structures before we even touch a patient. So today, so let's explore how engineers and dentists are collaborating using this powerful tool, combining biology, material science, and virtual simulation to improve the treatments, reduce failures, and ultimately enhance patients' outcomes. So let's dive into this exciting intersection of engineering and dentistry. All right. So just to give you a basic idea, like to solve any engineering problem, so whether it's in a civil or mechanical or a biomedical field, we typically rely on one of three core methods. That is analytical method. So these are based on solving mathematical equations derived from physical laws like stress strain relations or heat transfer equations. While they provide exact solutions, they're only practical for simple geometries and boundary conditions. Okay, and the experimental method, these involves physical testing of components or systems. Though they offer real world validation, they can be expensive, time consuming, and sometimes unfeasible for internal structures like the human jaw or tooth roots, right? So here comes the numerical method. So these bridge the gap. So here we approximate the solution to a physical problem using a computational models. So this is where engineering simulation enters the picture. So under numerical methods, we have four verticals, that is FEM, BEM, FEM, and FDM. So I'll not talk about the other verticals, but let me only focus on FEM. So finite element method, which discretizes the geometry into small elements and solves governing equation over those elements. So it's especially powerful for stress strain analysis in complex structures, which makes it ideal for dental biomechanics. So among these, FEM is the most versatile and widely used in the dentistry. So it allows us to simulate and predict the behavior of the teeth, implants, bone, and prosthetics under real world conditions without even the need of an invasive testing, right? Well, so let's understand fundamental concepts in engineering simulation. So how we represent a real life object in a computer model, right? So on the left, you see a real person sitting on a stool, right? So this is what we call the continuous approach. So in this physical world, all components like bones, muscles, and teeth are continuous, right? So that means their material properties and behavior vary smoothly and infinitely across their volume. So but you analyze this behavior using computer, we need to simplify the and convert it into a format that can be solved numerically. So on the right, we see the discrete approach. Here, the same structure is represented using a mathematical model mode of a smaller interconnected elements. So these elements could be triangle or quadrilateral or 3D tetrahedral, depending on the problem. So maybe I can explain it in while I demo the ANSYS. So this transformation from real life continuous body to a mesh of discrete elements is what we call a finite element method. So this approach allows us to study how a tooth, an implant, or even a full jaw structure behaves under various forces, even without needing to physically test it every time, right? So in summary, like the continuous model represents the reality, but the discrete model helps us analyze it in computationally. So to sum up, FEA, CAE, or they are numerical and approximate methods that use mathematical models to represent a real-world engineering problems. So they allow us to analyze complex systems efficiently by breaking them down into smaller smaller parts, and they are then internally connected with the nodes, and then defining the boundary conditions and loads and solving them with the computer simulation. Okay, so when come to the software-based simulations, so first we have to have a geometry. Typically, it is in a 2D or 3D. In dentistry, we rely on 3D models. So either they are created in the CAD modeling software by measuring the physical model, or we scan an exact jaw or exact dental model with the CBCT scan, and then we extract the nodal points, coordinate points, and then create a complex 3D geometry. So that is a prerequisite. So then we have a material properties, then we apply a boundary condition, then we apply external forces. So comprising all this makes a finite element model, and then we solve the FE model to get a stress, strain, deformation, and other interested results. So this is an elaborated workflow how a typical FEA process undergoes. Like we have a card model, do the meshing, do the connection, define the connection, either it is a node to node or it's a contact, then define the boundary conditions, then do a finite element analysis and extract the results. Okay, so just to have a connection between a mechanical engineer and the dentist specialist, so I took an example of a car, right? So here on your left, you see a CAD model where I have a fuel tank, front door assembly, hood assembly, engine assembly, rear chassis, and bumper assembly, and the deck lid assembly. So these are all the different parts in a car, right? They are manufactured or they are designed separately, and they are put together, and one complete full vehicle model will be subjected to FE analysis. And then we do the analysis and look at the results. So like if I am manufacturing a Mercedes Benz or a BMW, I cannot keep on doing a crash test on a real model, isn't it? It's an expensive affair. So I arrive at one final model, so that I will subject that to a crash simulation. So it saves a lot of money, it saves a time. Then the results are predictive, the failures are predictive. Then we arrive at one final design. So similarly, we can do any number of iterations in virtual setup, that is finite element analysis using finite element software. So similarly, we can do any number of iterations, any number of models virtually before even we create an actual model. Okay, so just for your information, so areas of applications are vast. FEA has applications in automotive, marine, energy, defense, everywhere. It has its applications everywhere, and it's in medical equipments and biomedical is also it is booming. So it is one of its application we are going to study today. Well, I am going to present three analysis today. So I will demo through presentation, as well as I will take you to the tool that we use to do all this activity, that is ANSYS. So we are using ANSYS software to do that. So before that, so this is one of the periodontic study that we have done. This is a baby tooth or the milk tooth problem. So first, like I told, the CAD, we receive a CAD model from a CAD engineer. So there is a dedicated engineer who creates a CAD model, right? So he shares us he will complete the CAD model and he share it to us. Then we do the activity called meshing. So where the infinite model is converted into finite models by breaking this into smaller, pieces, right? Then there are different types of elements. So here we have, in this particular study, we have used first order tetrahedral elements, and we always need to keep a count of elements and node count. So once here, if I can mm, show you, say maybe this is one triangle. This is a shape of a element. So this is called as an element, and different elements are connected at one point called nodes. So this count is very crucial in any FEA simulation. So if I can mesh, I can create, I can split the same model into million parts or in the thousands, right? I can split into millions or thousands. As a more number of element or no more number of node, the in proportionally the solution time will also takes longer. So we have to strike a balance between the element and node count and the result accuracy. The more the number of element and node count, more the accuracy, of course, but longer will be the solving time, right? So we have to strike a balance between them. Then we have I have just listed few of the material properties that we have used in here. So typically we current study is a we assume that the material is isotropic. Yes, some Dr. Siddharth has highlighted that, yeah, we have to move ahead and concentrate on the anisotropic and all other non-linear material types. Yes, that's expensive currently, and it takes a lot of time, and we should have a precise material properties to do all those studies. Yes, but currently we are restricting to assumption that we are using isotropic material here. When we model a finite element model, when we mesh, we just name different component with a different colors, so that it is easy for identification, and also we mark them while we mark them, and we keep them in a separate collectors or components we call, and assign respective materials to them. So here this slide just show you that we have subjected this model to two types of forces. That one force is in 100. I mean, we have applied 100 Newton forces. One is long axis to the tooth, and other force to the inclined to the palatal surfaces of the tooth. Okay. So we should have first like after the CAD model, we do the meshing, and then we have to define a fixed model, or else we have to define the boundary condition. So first approach in defining the boundary condition is we have to fix it. Like the model in the software is like it is in an open space. If we do not apply a fixed condition, if we just apply force, it just keep on moving in open space. So we have to restrict it, right? So we have to apply a boundary condition. Then we have applied 100 Newton forces in the long axis in this example. Then we give the model to the solver, and then we do the simulation. So then the output of the simulation would be in terms of displacements, like we here, as you can see, displacement plot and overall stress plot. As you can see here, so we get a contour plot like this, right? Here the color ranges, this we called as a legend. The color varies from blue to red. So blue indicates the lowest value and red indicates the maximum value. In the deformation case, here the zero displacement, where we had fixed the model, it experiences a zero displacement, and the end where we have applied forces experiences maximum displacement. So in the terms of stresses, the zero means low stress or zero stress. The blue color means, the red color means the maximum stress. So in this example, since the model is fixed at this end and applied load at this end, so we experience displacement more at this, and stresses we experience more at some junctures, right? I will move to the software to show how this simple study has been done, right? So this is a typical ANSYS software, the way how it looks. So we bring a model from external model. I mean, sometimes what happens, the geometrics are so complicated that sometimes we face a lot of challenges while creating a finite element model. So in that scenario, we rely on a couple of external softwares. So while creating a geometry, we use some famous commercial softwares like SolidWorks, CATIA, so to create a solid model, and then do a meshing in some famous softwares, Hypermesh or ANSA. We create a finite element model externally than doing it in ANSYS, or we could potentially do it in ANSYS as well. But most of the times, due to the unconventional shapes of the geometries, we do it with a dedicated specialized software. Then bring it to the ANSYS workbench. The first step is to define the materials. So here we have defined different materials that are involved in this study, like cancellous bone, composite covalx, and cortical bone, enamel, dentin post, gingiva. So all materials with the different material properties like Young's modulus and Poisson's ratios have been defined here, right? Then, so I will load the geometry. As you can see, this is a geometry. This is a 3D model. So I hope that you can see that I am rotating the model and visualize it in different orientation, right? So this is a geometry that comes up the moment I import it. Then I define the different materials that I am going to assign to each parts, right? I have the material properties. Then coordinate systems. So I can create coordinate systems. I will always have one global coordinate system, but depending on the need, depending on the orientation of the model, so I can create my own coordinate system, the local coordinate system, to define the loads in particular direction. So in this case, I need to apply 100 newtons of force in long axis. So here in my case, I have created this local coordinate system. My long axis is the z axis, right? So I need to define a forces in this, apply a force in z direction. So that is the objective of creating this local coordinate systems. So then comes to contact definition. So this is very crucial. Like, though I have created a model with the different layers of different components, I have to make sure that those components are interconnected. So for that reason, we define the bonded contact between each parts, right? So here, as you can see, this part is in contact with this part. So like that, we have several, like all the components, all the parts in this assembly are interconnected. So we have to define those connections, right? So once that connection is done, so we have to create a mesh. So this is how a typical meshed model looks like. So if I can go on hide, so they are all different parts inside, right? Maybe I can do one thing. I can split this up. Well, I can show that maybe later. Okay, not a problem. So this is a mesh model. So we convert that infinite model into finite model by splitting them into different parts, different zones. So now the main important part is, like, we have to check the statistics of this, like I mentioned. So we have to keep an eye on the count of elements and node. So like I previously mentioned, so we have to strike a balance between the count and the solution time. So what I mean the solution time, like when I do a setup, I run the software, I run the simulation in the ANSYS software. So the solution time ranges from minutes to hours to even days. So more the complex the problem, the more it takes time. So we have to make sure that we maintain optimal element sizes to make sure that our solution runs within a desired time and also provides some favorable results, right? So once we complete the meshing, so we have to define a solution type, what solution we are going to run. So here in this case, we are running a structural simulation, right? This is a static structural simulation we are going to execute on this model. and we had, like I said, we have to define. So we have the geometry, we have assigned the material properties for the respective components, we have even defined the coordinate systems, we have defined the connections, then we have done the meshing. It is in sequence, so we have to complete each activity to get the solution. So then next steps comes to the fixing the support, applying the boundary conditions. So here the region what you see is being fixed. We have arrested this region for all the 6 degrees of freedom. Like when I talk about 6 degrees of freedom, so typically we will, for each axis XYZ, we will have 6 degrees of freedom, three translational and three rotational degrees of freedom. So we have to arrest all of them. So we have selected this phase and arrested the degrees of freedom, then apply the force. So we have defined the force. By selecting this phase, we are applying the force at this phase in Z direction. That's why I have defined 100 Newton forces in Z component direction, right? Then we right click and click. I mean, we solve it for the solution for the defined geometry, material properties, connections, and all the aspects of it. Then after running, we get a solution. So these are all the result types that I have requested ANSYS to provide after solving. So it is not like you define everything and click solve and you get the solution. So there are challenges we face during the solution. Like sometimes mesh don't converge. We have to remesh certain areas. We have to refine the meshing at particular areas. Then we may have to change the material property. We have to make sure that the material properties are properly defined, or the contact definitions are properly defined. Then when we hit run, so it takes time. Like I said, it may take minutes or hours or days depending on the complexities. If I take an example of the car assembly that I have shown previously, it will take around 2 to 3 days to solve a small crash simulation, right? Depending on the computer hardware as well. With this advancement in the computer hardware, so now since we have a most sophisticated hardware, so we were able to get the solution in less than a day or so for the complex problems. For smaller problems like this, these solutions will be completed within 30 minutes or maximum 1 hour or so, right? So this is the deformation plot. I can go on clicking after requesting different types of results. I can go on clicking the solution that I have extracted. So here in this case, I have asked ANSYS to provide a total deformation. So the deformation for this load case, for this force application, I got around 0.03 mm, right? So in bare eyes, it is very difficult to visualize the 0.03 mm, right? But in FEA, so we can visualize, we can see the animation, right? So if I can show you the animation. As you can visualize, so I can also look at the animation in the software. I can understand how my structure is behaving, how the stress and deformation is transmitting into the entire assembly, right? So this is the advantage I have in the ANSYS, right? So, and one more advantage is, like, I can do a cross section. Say I have a predefined cross sections here, so I can cut the model into pieces in different orientations, different directions, and visualize internally also how the deformation is, uh, happening, how the deformation happening, how the stresses are distributing in different zones of the components, right? So this is one of the approach how, we that's the advantage what we get in ANSYS. Similarly, if I can go back to my slide, so this is a comprehensive FEA report that we prepare after doing a simulation to give a more insight of different component, different types of results in different parts, different way of putting the things. So here we had put a maximum stress distribution study across the part by putting a cross section, and we also go each component wise. Like here in the gingiva bone, we wanted to see how much is the stress in the cortical bone, in the cancellous bone, okay, and also in the PDL, in the dentine, in the zinc oxide, agonal, the post and zirconia crown, the composite core. So likewise, we can extract the values of stresses or deformation and each individual component. By that, we will understand how the stress distribution is happening across the parts, across the components with that applied forces, right? So this is one of the study. So coming to this analysis to orthodontics. So we have an upper jaw with the aligner, right? We have done the simulation for the same. We wanted to understand the retraction forces, so and how the stresses and deformation distributes across the assembly. So we have applied 100 grams of force on each tooth, right? That is, the aligner is applying that 100 grams of force. It is, bringing all, it is pulling all the tooth back. So we wanted to analyze that effect. So we have applied 100 grams on each force, and we have done the meshing of this assembly, and you can see the different orientation of the images and the node and element count. And these are all the material properties that we have used. Similarly, maybe I can go back to the software and I can show you the same model. I have already did the simulation before this presentation because this activity will take a lot of time and effort. So just to save time, I do not wanted to execute in the session. So I have already done this activity before, and I have also solved them to show you the results. So this is the actual model with aligner, right? So this portion is aligner that we have created, right? So this is the entire jaw. Similarly, we have the geometry, material properties assigned, coordinate system defined, connections defined. We have the meshed model, right? And we have defined the static structural analysis. We have defined the fixed condition at the top. The top face has been completely fixed in all 6 degrees of freedom, and we have applied forces on each tooth, which aligner in implants, right? So then we solve this problem and requested for different types of results. So here we got a deformation, as you can see. We can also play an animation to understand how exactly the structure behaves after the application of the forces. And we have looked at the stress values at different regions. So the one advantage is in ANSYS is that say, in this current part, say this is PDL part, which I am looking at this. So if I am interested in knowing the stresses or deformation,
Noise, you see there is a noise. Okay, thank you.
Right. So in this study, say for example, my area of interest is PDL. I want to understand, I want to see how the stress distribution is happening in this particular component and how the deformation is happening. So I can only keep that part and plot the result for that. So I can understand that the stresses in this particular part is varying from like 0. In microns, it is in 0.0036 mm, sorry, megapascal to 0.18683 MPa. You can see this legend will give you the enough information like this is a static structural analysis we are doing, and we are plotting the equivalent stress and that equivalent stresses. We have different types of stresses. We have principal stresses, one measure stresses, normal stresses, shear stresses, right? But in comprehensive, we typically plot one measure stress to understand the critical areas, and the unit is in megapascal, or you can define it as a Newton per mm square. Right. So, and I can appreciate it. I can zoom in. I can go to that particular location and see how much is my stress value here. Whether, and in most of the scenarios, the stress values what the software defines may not be true, or may not be accurate. So it comes with years of experience and judgment. Uh, like some ma'am has highlighted in her presentation that you have to be very cautious about the what inputs you give, what boundary conditions you define, right? It is like FA is like garbage in, garbage out. So you provide wrong information, anyway it will solve it. If the solution solves, it doesn't mean that the results are accurate. You have to make sure that your inputs are also accurate, and your mesh is also accurate. Your contact definitions are accurate. Your boundary conditions should be more realistic, right? So when we do a physical test with the compare with the FES test, so it should be in the range of, previously it used to be the accuracy, it used to be between 80%, 85%. But now with the advancement of algorithms, with the advancement in the hardware systems, the accuracy margin has increased or it has crossed beyond 90%. So if my results are matching with the physical testing with the FEM, analysis, which lies between 90%, then we call it as a very good study, right? So we have to have that error margin always counted. So I can plot the stresses or displacement for different components like this. So I can go on, visualize them, zoom in, look at those areas like where exactly the stress distribution is happening, whether it is a genuine stress or it's a spurious stress, it's a localized stress. Sometimes, say for example, in this scenario, so we may not count this 0.28 MPa because it is somewhere lying inside and it is a the stress is occurring at a very small portion, small area. In such scenarios, we look at the areas which are having a larger distribution. Say, if I am asked to tell what is the stress in this central incisor, so I can go and check, I can rotate the model and visualize it and see which is the highest, which is the color which is distributed in the larger area. So I can take this is a color which is distributed in the larger area, so I can go and refer to the legend that my stress distribution at this central incisor is around 0.1873 MPa. So that is how we do a interpretation, result interpretation, when we after doing a simulation, right? So likewise, we have plotted results for different parts based on the customer requirement, based on the doctor's inputs, and we extract the results, and we evaluate and provide a proper conclusion of the study. Right. So coming to one more prosthodontics analysis, the third simulation what we have done. This is pretty interesting one. So here we have done a lower jaw with all the corresponding parts included. But you might question why we have a half part, right? So like I said earlier, the more the complex the geometry, the more meshing time, the more the mesh count, the more the analysis time. So to save that, in most of the scenarios, this will be axis symmetry, right? We assume that the other part is also reflected. It's like it is same. So that's why we do a concept called symmetric concept, where we do not model the entire model. We just split it into half. We have to find whether it is a symmetric or not in the first place. So once we find that okay, this is symmetric, then we do only half of it, cut it into half, then do a meshing and all the other activities that I have explained. So now you can see the node count and the element count. It would double if I model a complete model, right? Right. So this is a area where I'm completely fixing it, and this is a face. I'm defining it as a symmetric region. The solver or the software understand that the same model will be reflected. Same model exists the other side. So we don't actually need that model in reality. We just define it as a symmetric region. Right. So here we have applied two forces. Okay, one is 100 newtons vertical and 100 newtons inclined, 15-degree inclined to the vertical axis. So these are all the two forces that we have applied at a tooth. As I can show you. So this is a deformation plot. This is the animation that you can see. So we can extract the animation and we can put it in the PPT to visualize while sending it across to the stakeholders. We provide all possible information so that they can take a call, they can take a judgment on their design, whether the design is coming in the way how we are expected, or do we need to change the material, or do we need to change the design, or do we need to use a different material altogether, right? So this is a study that we can do using the FEA tool. So here in this study we went on
Rahul, can
extracting
you
different.
mute Govind sir? Can you mute Govind sir? Okay. Yeah. Thank you.
All right. So in the similar to the previous studies, so we went on plotting the different parts. We extracted different results for regions like PDL, cortical bone, cancellous, and teeth regions, right? So in the implants, in the abutment, in the crown region. So maybe I can show that in this tool as well for the better visualization and understanding. Excuse me. Yes. Like I said, so the other part of the, since the geometry is symmetric, so we did not go ahead with the complete mesh. We splitted it here and did all the meshing activities and the sim setup. The process goes by the similar way. Like we have to define all the parameters, all the attributes to be ticked green. As you can see, the status here, the green. We have to make sure that every status is all the status of the geometry, material, coordinate system, connections, and mesh, everything is turned into green. Then we define the analysis type, and we define the boundary condition. We apply the forces. So in this case, we have selected this face and applied vertical 100 newtons, and we have created the local coordinate system which is inclined in a 15-degree inclination, and applied a force in minus z direction. Right? Then we solve it, and we get the results. Maybe I do not have a results in this. Let me quickly solve it. We'll see whether it will solve or not. So until here, the user has to define all the parameters and make sure that we don't commit any mistakes in while defining any of those required fields for the analysis to run. So once we hit on solve, so the solver will take its time depending on the complexity and depending on the number of requests or number of results that have been requested. So it and also depending on the hardware that we have, it takes time to solve. Maybe I'll skip that part to save some time. I will just jump into the PPT where the model has been already solved. Like I have already shown, these are all the results that we got from the ANSYS software, where we extracted results for each individual parts, or we can extract the results as a one complete assembly and look at the areas where we are getting maximum stresses, maximum displacement, and also we can go and look at each individual components and study, because say in this PDL component we have applied the material properties for the PDL, right? In the cortical bone we have applied cortical bone properties, and in the abutment we might have used some titanium or some other materials we might have used. So after the study, we come to know that this part is getting a maximum stress of 75.614. So maybe this is not the stress that we were looking. We wanted to bring down the stress. In that case, what we have to do? We are left with options like we can take a call of changing a material or changing the design altogether or changing the way it has been placed, so that the after getting the results, it gives us a numerous options to take a call whether to change all these options, and then redo a iteration to understand whether stresses or displacement has come down or they have increased. So based on that, you can take a call, and then you can arrive at one final prototype, and eventually you can go ahead and put it in actual patient. And you by doing all these studies, you will have a backed up study, you have a parameters studied in detail, so that you are confident about the outcome and the parts that you are going to put it in an actual patient. Right. So this is all about the FEA and the setup and the simulation activity that we do. The possibilities are numerous. We can subject any, and then we can do any kind of a study using the FEA software. It is not only restricted to the examples that I have shown. We can do any and every study that is related to dentistry using the FEA software. So if you have any doubt, any questions, you can kindly ask. Thank you.
Hi, thanks, Rahul, for showing us and traversing us towards the dental FEM analysis with the software as well. So now the platform is open for everyone, and I request they can raise anything to discuss any query which they have. We are here to take those queries, and we can move forward. I think there were some queries were sent to Abhilasha to our group as well. So Abhilasha ma'am, do you have any query which we can brought to this platform and discuss, or we would like audience if they want to raise or anything they want to ask, you're really welcome for that.
Yes. So as of now, I can read one question. What is more important, whether the material property in the FEA analysis or the node counter element, which is having the more effect on the study?
I would say both actually, ma'am. The first and foremost, the most critical one is material properties, of course. So the material property has to be very accurate. We have to be sure that the material properties that we are using are more accurate and near to the reality. And we have to do a mesh sensitivity analysis to arrive at a right node and element count. Say for example, we have to do a couple of iterations by varying the node and element count. We have to make sure that, say for example, I have meshed my model with 1,000 elements, and then in next instance I have modeled my model with 1,100 elements. I have to make sure that the results for 1,000 elements and results for 1,100 elements should be same, or more or less it should be in the same range. Then I understand that I have reached that mesh sensitivity and my chosen element count or node count is correct. So that is where I stop doing iterations, and then I'll pick that element size and go ahead with the analysis.
Okay, fair enough. The next question, what we are able to see is they're asking that how we define the bone density.
Well, that is through the material properties. We have parameters called Young's modulus, Poisson's ratio, and also material density. We can define a material density through a kg per mm meter cube or mm cube. So that is a density value we have to put into the software so that it will accommodate the bone density value.
Okay. Next question, what I'm able to see is how it will be possible to do the analysis near to the clinical practice. That means it's supposed to be more of the actual study. Actual instances that what are in day-to-day life, what are patients supposed to feel. So through the study, how we can imitate it more closer to the same.
Absolutely. Like I said in the earlier stage, if a patient comes up with particular problem, so if the patient has to undergo an implant, we have to insert an implant in his dental. We have an option of taking a CBCT scan of the actual patients. Then we can replicate this. We can generate a 3D model out of it, and we do a simulation in the software using different implants and study the stress values, deformation values. We can apply the actual bite force. We can see how exactly the entire assembly behaves, and we can pick a right implant for that particular patient.
Okay. But and then next question, Rahul, which I'm able to see is, can you define the key factor while doing the FEM analysis?
Key factors in the sense, can the question be little elaborative?
Yeah, it is more like what I'm able to understand as of now, like what are the factors or the the points which you need to keep in mind while doing the analysis. What all points or the factors are more important while doing this?
Right. Whenever a dental professional decides to go ahead with a finite element analysis, so first he has to make sure that it starts from the geometry, right? So whether the geometry can be physically measured and modeled, or it has to undergo a CBCT scan and then we create a model. So we have to start with that concept. Then we start accumulating the right material properties. We have to refer many articles, or we may have to go to a material testing lab and get the material properties tested and note down the values. There are many studies that have been already done, so we need not do that exercises. We can refer to some good articles, fetch the regular material properties that we have. Then we have to arrive at the forces. Then that's it. Those are the parameters from the dental professional we need to get as a so rest
next question, Rahul.
We will take.
What I'm able to read is from Dr. Sajid. He's asking that I conducted an FEA study, but I encountered a difficulty. My technician informed me that he couldn't simulate tooth and jaw movement using the ANSYS software. I would like to know how I can effectively simulate these movements.
Yeah, there are several factors for a successful analysis to happen. Like if I mess up with the material properties, if I define some very soft material and then define some 100 newtons of force, then the model will run away, right? And I have to make sure that I define a proper boundary conditions. My forces should be proper, and the majority of the issues comes in the contact definition, right? Where how the each individual components are connected to each other, how and also the meshing, how well my mesh is defined. So there are set of principles, set of rules, guidelines we need to follow while creating a mesh. The element size, the mesh sensitivity, the node and element count, and whether I should do a fine meshing or coarse meshing, which element type I should use, which element order I should use. So those are the technicalities. If those we typically have a checklist. Okay, then if that checklist is passed, then it is obvious that we'll get a 100% result.
So we do have a freedom to check the movement of the tooth and the jaw.
Yes, absolutely,
well, right?
Absolutely.
Okay. Any other question you would like to ask? We are here to answer you. If any challenges which you have faced over the period of time while planning your FEA or doing the FEA simulation. Any other question? Okay, as of now, I'm not able to see any more query. But still, we are open for the same. If any query you people are carrying with you, or any question or any discussion for the FEA, so we are there. You can drop a mail for the same, or maybe we can WhatsApp us on the below numbers. So thank you very much for each and everyone. I would again like to thank few of my guests again, Dr. Namita Kalra, Dr. Chandrika Savarkati, Dr. Rita Jain, Kumar Amit, and Dr. Siddhartha S.P. Behera. All of us are here to have the insight of the dental fee analysis. And ma'am and sir, thank you so much for joining us and give us such a beautiful insight of the FEA analysis and your SME into the same, and what you are able to see into the clinical practice on the day-to-day life. It is very insightful, it is very knowledgeable, and it was fruitful, I will be saying. But we learn from each other. So this was such a good session we all were having. Thank you so much for joining us. Thank you, Chandrika ma'am. Thank you, Rita ma'am. And I'm able to see any other person who is among our guests. Govind sir is there.
Oh,
Thank you, everyone. Thanks a lot. Have a good day.
Thank you. Thanks a lot. Thanks, everyone. Thank you.